variable for one person is higher than the one for another, for a person from another group, but the difference of the group averages at the opposite side. So basically, that's of course that happens all the time. It's not something surprising in any way, shape, or form. But the intention, I suppose, of Gini was to somehow quantify this. So he referred to this as transvariation. That is variation that happens across boundaries of the definition of groups. Now we don't have any mean values that enter the picture here because all we've already at the end of the day is numbers of people. But to us it seems there's a very natural notion of transvariation that we can define in this context, and that is because as you can see here, it happens very quickly. It happens very quickly that the set of the top wealth people and the set of lowest wealth people overlap when you want to find how many of the low incomes you need to low wealth people you need to compensate for the top ones. And you can, to us it seems quite natural to think of the size of this overlap as an indicator of transvariation. Basically what transvariation, I think of as transvariation to some extent is some sort of cross-contamination, right? You do something that spills over boundaries of groups. And that is, by definition, of course, closely related to this definition of concentration. And in what we think again is perhaps some observation of some historical interest, we can show that the two are actually equivalent. I'll talk a little bit about how we prove this. The proof method it's not rocket science by any means. Basically what we do is essentially based on inequalities, right? But don't knock inequalities, right? They have a long-standing tradition of being very important tools in the analysis of economic index numbers, or much more generally in statistics and mathematics. Hardy and Polya read a whole book on inequalities. Any notion of majorization is based on inequalities. Any notion of curvature, quasi-concavity, concavity, etc. You cannot get by without it. So in that sense, the techniques we use in our group are very pedestrian. It's not, again, we don't involve any very deep and complex methods. But we do use, again, we just multiply inequalities, we combine them, and in that sense, it also makes what I think makes the proofs quite intuitive and transparent. So, but let's first define transvariation in our context. And one way of doing that is, well, essentially you look at the overlap that could occur in these inequalities. So let's define another variable r, or another function, for a given distribution and the number of wealthiest. And this function will be defined as the overlap in all these comparisons. So basically, if the set of low wealth individuals you need to compensate for the high wealth individuals does not include any of the high wealth individuals, the overlap is 0. So you have 0. If it is the case, that the difference between the number you need and to get to the aggregate wealth of T is less than root n minus T. There is no overlap, so it's 0. And if you do need some people that are also in the wealthy group in order to determine how many of the low wealth people of the top wealthy group, I should say, of the low wealth people you need, if there is an overlap, then clearly this becomes positive. In that case, you get the number of low wealth people you need minus n minus T. If this number exceeds n minus T. This is very simple. Here's a diagrammatic illustration. Individual 1, individual n, suppose we have a number of T of high wealth people. This is n minus T. If Q of y and T is located below n minus T, we get a 0 as our overlap. If on the other hand, we have a distribution, let's say Z, for which the set of people, of low wealth people, you need overlaps the set of the T high top wealth people, then of course you get a positive number. Now then you can define dominance relation in terms of transvariation. By saying the distribution y is in this relation, is in this transvariation relation to a distribution Z, if and only if we have this dominance relation on for Q and for R. Now, a few things are immediately obvious. What you get right away is, by definition, that RC is contained in RT. That can be shown in very elementary means. And when I say elementary here, there's a precise way in which I can define this. Elementary in this case means you can do it 1T at a time. Right? If you have this relationship, if Q generates this inequality between y and z, R will generate this inequality. So that you can do with only looking at a given t at a time. Conversely, if you look at R, this function R, and we have a dominance relationship here, that does not immediately give you this set of inequalities. It does in one special case. If we have a situation in which, let's say, R of yt is greater than or equal to R of zt, and R of zyt is actually positive, that is true in this case, then again you get Q of yt is greater than Q of y of zt as well. You can do this immediately for a fixed t at a time. That's again elementary. Things become slightly more subtle if we have the other case. So suppose we have dominance according to this function R, according to this relation RT. But we are in a situation in which both R values are equal to 0. We have dominance for y over t, that is, if you look at all possible values of t, the y values will always dominate the z values. That's a special case with inequality, of course. In principle, just by looking at t, there's nothing that rules out that q goes in the opposite direction. Right? So this, by looking at t alone, you cannot rule this out. And so at first, when we looked at it, we said, well, that probably indicates that actually this subset relationship is strict. But it turns out it is not. But to show it, you have to go a little bit further and make use of the fact that these are dominance relationships. Right? That these things are not true just for one t in isolation, but they have to be true for all. Right? So this is slightly less, in that sense, it's slightly less elementary. Again, it's still not rocket science to prove it, but it means we have to do a little bit more work, and I can just give you a little illustration of how we proceed in this case. I don't give you the full proof because the full proof covers all possible cases, and I just want to give you an intuitive idea why this works. It's very simple, as you will see. Take an example or whatever, suppose. So this is just an illustration. Suppose we have 10 groups of individuals, and suppose we have a situation in which to 7. And suppose we have an unpleasantness of this nature. Let's see, for example, that we also have y1 plus y2 plus y3. 3 are not enough to match the two wealthiest, 7 and 8, but 4 are. Oops, sorry, this is less. And if we add the 4th lowest wealth recipients, we actually do get a situation where we match 7 and 8. Now, what does this tell us? Well, it tells us that Q of y and 2, we want to match the top two, the two wealthiest. We need 4. We also know that the R value of this distribution for 2 is equal to 0 because there is no